In this example, we are going to use linear approximation to get a rough idea of what the cube root of 2 is and the cube root of 26 is, right? And so that's what we're going to be looking to figure out. And this is our formula, and we are looking to approximate cube root of 2, cube root of 26, and we're going to figure out if they're overestimates or underestimates. And then we use a calculator to actually plug them in and see how accurate we are. So, in order to do this, we are going to need a slope equation. And so if our original equation is a cube root, let me write it as an x to the 1/3. And then if we do the derivative of it, first derivative of that, we're going to get a 1/3 x to the negative 2/3. Right? So there is our first derivative. Clean that up a little bit. Our first derivative is 1/3 x to the negative 2/3, which I'm going to rewrite that as a 1/3 times a cube root of x squared. Right. And then, so I'm going to use this one now to do the second derivative. The second derivative is what helps me figure out my overestimate or underestimate. That's the concavity piece. So whether something is concave down, our value that we're finding is a point on a tangent line, but the actual value should be a little bit lower. So we would have an overestimate on that situation and underestimate on the other situation. So we're going to kind of analyze what we got going on. What I need for that is the second derivative. So if I do a second derivative of this, we're looking at bringing the 2/3 down. So that'll be a negative 2/9. And then x to the negative 5/3. If I rewrite that, I'm looking at a negative 2/9 to the cube root of x to the 5th. Right. So I'm going to use that. Nothing crazy on that one, but I'm going to use it to figure out whether it's positive or negative to know if at that point it's concave up or concave down to kind of help me determine if it's overestimate or underestimate. So let's do the math now. So if we are trying to figure out what the cube root of 2 is, we need a nice value. Our x value is 2 for our formula. So our x value is 2. Our nice value is something that we can cube root that's close to 2, as close as we can get, which would be a 1. And then I'm going to start plugging things in. So my linear approximation at 2 is going to be the y value of our clean value. So if I cube root 1, and then I will be adding the slope at 1, which is this right here. So 1/3 times the cube root of 1 squared times our value that we're looking for minus our nice value. So this is going to get us an approximation. So this is 1 plus 1/3 times 1. So if we add that up, we're looking at 1 and 1/3, or approximately 1.333, on and on and on and on. So our approximation using this method is roughly 1.333. Okay, so we're going to figure out what the actual is here in a minute. So the next part of this is we need concavity. So I want to know if this approximation is going to be over or under. And so we're going to shift over to our second derivative and plug in our nice value, right? And so we're going to be plugging in the 1 to kind of figure out, are we close or not close? Is it going to be an overestimate or underestimate? I just need to know, what's your concavity at that nice point? Doesn't matter if we plug in a point further, might as well plug in a nicer point because we can cube root it. So all I care about is if it's positive or negative. So we need concavity concavity at 1. So concavity at 1 is us taking and plugging 1 into this. So we're looking at -2/9 times the cube root of 1 to the 5th. And all that is going to be a negative divided by a positive. So we're looking at a negative value. So -2/9, which that is concave down. So since that's concave down, right, that's our nice point. We have concave down. So the value that we should be getting is here, but the value we're getting because we're using this linear approximation is going to be a point on the tangent line, and it's going to be a little bit higher. So we have, because it's an concave down, we have an over estimate. Right? And then our last bit of this is, how does it compare? So the real value to this is if we take 1.333 and minus the actual cube root of 2, if we plug that into a calculator, we would get roughly 0.0734. That's how far over we are. Right, so close-ish. So let's do one more, all the same steps. So this time we're going to be figuring out what's the cube root of 26. So our x value is 26. Our nice value, our perfect cube that's close to it, is 27. We're going to do the exact same step. So we're going to be doing the linear approximation of 26. It's going to be us plugging 27 in. So it's going to look just like this. So we're cube rooting 27 plus 1 over this. We're doing the slope at 27. So 3 times the cube root of 27 squared. And then times 26, our x value. So 26 minus our place value. All right, so trying to figure out how to do this. So that square actually could be on the outside. So come back. So if we cube root 27, that's going to be a 3. And then if I cube root 27 and get a 3 and then square it, I get a 9. So 9 times 3 is going to be 1 over 27. Then times 26 minus 27 is a -1. And that means we're getting a 3 minus 1 over 27. And if I plug that into a calculator, I get about 2.963. So if I throw that in the calculator, that's what I get. So I'm estimating that the cube root of 26 is about that much. Okay, so there's my estimate. Right, and then I want to figure out concavity. At 27. So if I take 27 and plug it into the second derivative, here's my second derivative. I have a -2 over 9 times the cube root of 27 to the 5th. All right, I'm not even going to try to do all that math. All I care about is that this thing is going to turn out to be a negative value, which means concave down. So since it's concave down, we go back to this again. Concave down means I'm getting this value when in actuality it should be that value, right? So I am still getting an overestimate. Right, and actually, I guess we would be a value less than it. So we would be kind of more, we should be getting this value, but we're getting this value. So we're still over. So we have an overestimate going on. And then if I want to figure out how close are we, then I'm going to take the answer that we got, 2.963. 3. And if I subtract out the actual cube root of 26, we get approximately, we are 0.00047 off. So that time we are much, much, much closer. And it kind of has to do with the fact that the difference between 26 and 27, the bigger you go, yeah, the difference is still 1, but proportionally, they're much, much closer to each other than a 1 and a 2, right? They're like, that's 100% larger versus this is just a little bit larger. So, so that was doing some, using linear approximation to do some estimates at a couple different equations. Sometimes these values are going to be given to you, sometimes they won't, but whatever values you are starting with, you have some sort of an equation that you're trying to estimate, and then find values that are close. Once you find values that are close, you can kind of work through the math, and it doesn't totally necessarily need a calculator unless you get something that is kind of like, I don't really know what that is, but we could still have created a fractional version of that. But a decimal is much nicer so that you can actually like compare some things.